second half an hour. Okay, 12 to 2:15 to 9. Start.
Okay, I'm starting. Okay, right. So what you can see here is you can see, Michelle, just close that side window because of the lines, which is why I always open the other side window. Alright, okay, so what you can see is that these things, unlike in the previous one where I showed you, are not the same width the whole way up. And what does the increase in width show? It shows not number of organisms, it shows number of different types of organisms within that group. So it shows diversity, and that's critical because this is about diversity. Okay, so the wider this bar is, the greater the diversity within that group of organisms. And that's terribly, terribly important. So if I say to you, which is the most diverse group of organisms currently, dicotyledonous plants are slightly wider than monocots. Monocotyledonous, so I think it's probably dicotyledonous. Perhaps insects may allow us, but I do think that. So you might need to take a ruler and measure from there to there and just go, this one is more diverse than that group. Does that make sense? Yes.
Do you believe in the Big Bang?
I'm not clued up on it. It's not a field of interest for me. So
do you know, like, the people that do believe in it, like when it was?
The Big Bang, as in all organisms started?
Yeah.
No, I don't know.
Okay.
No, I have no idea.
Okay.
Okay. No.
Now this document is already on PowerPoint, right? Just to make sure.
The PowerPoint.
Yeah.
Yes.
Thank you.
Okay. All right. So you happy with that? What can you tell here? You can tell whether organisms are extinct or not. And if you look here, you can see that group of organisms is extinct and that group of organisms is extinct. And so are the trilobites, etc., etc. Okay, you know how to tell that. Okay, but then another critical thing that this shows you is it shows you when the mass extinctions occurred. So remember you learnt in grade 10 about mass extinctions. So there are 5 times in the history of this earth where certain events have occurred that made many groups of organisms become extinct, or many different types of organisms within a group became extinct. So let's say, for example, you're talking about insects. Maybe many types of insects became extinct at that time because environmental conditions changed so markedly that certain organisms couldn't remain alive. And you learnt about those in grade 10. So, for example, one of them they think was a big meteorite that hit the earth. And while you think, you know, who cares about a big meteorite hitting something in Mexico, hitting the earth in Mexico? Sorry, guys, no COVID. Why would that make organisms become extinct? And what happens is that clouds of dust and ash go up into the atmosphere. And they linger in the atmosphere for an advanced period of time. So what it means is that there's this layer which prevents light rays from hitting the earth. So firstly, it becomes incredibly cold during that period of time. And secondly, it means that the plants don't have enough light to photosynthesize effectively. And therefore, the levels of oxygen in the atmosphere would probably also decrease. And that means that certain groups of organisms that require certain conditions of temperature, etc., no longer exist. So there were 5 mass extinctions. Remember that they believe that we're going through the 6th. And that the 6th one is caused by humans. So because we're causing like global warming and all that kind of stuff, that organisms are becoming extinct at a great rate. I think, if I remember correctly, it's 1 every 20 seconds, one kind of organism. I think, but I may well be wrong. Okay, so what you can see here is I can say to you, tell me when the mass extinctions occurred. And you can see at least 2 of them here. So what you can see is at the end of the Permian, beginning of the Triassic, which is why it went on to a different time period. Look how that's gone narrow, that became extinct. That one's narrowed, blah, blah, blah. So the number of different kinds of organisms within that group decreased significantly. So here, for example, if you look at amphibians, the number of different types of amphibians probably decreased by 2/3. Because if you take the width there and you take the width that exists, this and this and this are almost identical. So you can say the number of different types of amphibians decreased by approximately 2/3. Okay, etc., etc. Okay, and then this one is obviously also a mass extinction here. Is there. Okay, so you can see nicely at least 2 of them. Alright, you happy with kite diagrams? You know how to do it. But please remember, this is the number of different kinds of organisms within that group. Okay, it's not the number of individuals. Okay, and then this is just exactly the same thing, but showing you in more detail and a greater magnification. So if I say to you, when did mosses and liverworts evolve? You would take a ruler, you would go up, and you would work it out carefully here. And nice and carefully, guys. Okay. You know about the current classification of living organisms, that we work on 3 domains, eubacteria, archaea, and eukarya. Don't obsess. But they all come from a common, universal common ancestor. Okay. And that they have evolved. And so this would be a phylogenetic tree. Okay. You have to understand about the evolution of the horse as an example of how the fossil record shows that evolution occurred. Okay. There's lots of fossils which show the evolution of a horse.
Do we have to know the actual example, or do we just find something? Do we have to say?
You have to know an example, and this is a good one. Okay, so what I'm going to do is I'm going to show you what actually happened in terms of horses. So this is the geological time scale from long ago to now, and this shows you this is the organism from which it evolved, Hyracotherium, which may or may not be pronounced like that, may be pronounced totally differently. And here's the modern horse, which is Equus. Okay, so what actually happened is the ancestors lived in forests. Now you know that it's problematic to walk through forests because you hit your head on things, etc. And so the ancestors were really, really tiny, 0.4 meters. Okay, and 0.4 meters means your ruler and a little bit longer. Okay, so it's not very tall at all. So they were tiny, tiny little organisms. And on their feet, okay, there were 5 toes. One had already, there's a word for it. Okay, one had already disappeared. Okay, so 5 digits, and this is going to be important. So what's going to be important is the height of the organism, the teeth of the organism, and its toes. And do you guys know that horses walk on one toe? Okay, so horses walk on their middle toe. So what actually happened is, over time, they rose higher and higher and higher. And the reason why all these changes occurred was because of the change of the environment. The forests disappeared and they were replaced by grassland. So instead of being forests, there were now tall grasses. So that poor little tiny horse that was only 0.4 meters wouldn't be able to survive in grassland because it couldn't see any predators, because it's busy trying to work its way through all the grass, which is much taller than it is. It's like me walking down the corridor. Can't see anything other than your knees. Okay, so that poor little tiny horse, when the environment changed and the vegetation changed to being a grassland, couldn't see over the grass. So it evolved to be taller, and B, one of the ways that it worked around this was it started to walk on tiptoes. Okay, so it started to go higher and higher and higher and higher on its toes. And these two digits are shorter than the others. So when rising up on the toes, what would be the longest digit? It would be the middle one. Okay, so eventually, at one stage it was walking on 3 digits, and then it walked on only the middle digit. And that's what horses walk on now. Their middle toe, and the hoof of a horse is its nail. So it's a nail of the middle toe. Okay, so it goes from being, it had a pretty good digit 2 and 3 and 4, and number 5 was quite short and it was on the side. And this is all about energy. There's very little point in using energy to produce and maintain something that is of no value. Okay, very little point. Because to produce something and to maintain a body part that has no value at all requires eating more. Okay, because then you've got to eat to maintain that part. You've got to keep more energy, keep getting energy to maintain that part. It's like you guys. When you turn 18, your parents are going to open the front door and they're going to put their foot on the small of your back and they're going to say, get out. So they wasted energy producing you. Why should they maintain you? Okay, because all they've got to do is eat and work hell of a hard to maintain you little brats. So push you out. Or better still, have used contraceptives there. Because if you use contraceptives there, you don't have to produce them and you don't have to maintain them at all. It would have saved them a lot of money and a lot of energy. Okay, do you understand that? And that's what evolution is all about. A lot of evolution is about saving energy. Don't produce things you don't need. Don't maintain things you don't need. Because all of that saves energy. So turn on digit number 5. Waste of energy. This is your first child. Get rid of it. Please don't say that in a test or exam. Okay, so that eventually was no longer produced. It became what is known as a vestigial organ. So at that stage of the game, there's the remnants of digit 5. But look, here it's totally gone. And digit 2 and 3, 2 and 4, starting to be your teenagers. You need to get rid of them. Okay, modern horse, tiny little bone, which is a remnant of 2 and 4, walk on 3, the rest of them is gone. Okay, they don't exist anymore. So there's that. The horse is much bigger. Modern day horse, 1.6 meters as opposed to 0.4. Can definitely look out over grasslands and see potential predators. Does it need to be able to see food? No, because it's not a predator, it eats grass. Okay, so there's grass there, eats the grass. So just be careful how you express the height thing, that you're able to see potential predators before they reach the horse so that it can take avoidance strategies. And then the other thing is the development of the teeth. So if you look at the teeth were very, very tiny, and they had a very, very thin layer of enamel, which is the hard part over the teeth, because they ate soft vegetation in the forest. But grass is hard, and grass has very little nutrition and it requires a huge amount of chewing, and therefore the teeth are much bigger, and the teeth have got a very thick layer of enamel, so that they can actually chew that hard grass to get the nutrients out of the hard grass. And so what happens in older horses, you know that to age a horse, what do? Look at its teeth. Why? Because the food that it eats weighs down the tooth. So the older a horse is, the more the tooth has changed from being like that to being like that. Okay, you happy? But the teeth are these little things, the horse ancestor, very tiny. Okay, so blah, 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 blah. Okay. Second category of evidence for evolution, descent with modification. And I've explained this one already to you. Okay, all right. And so, modern technology has allowed genomes to be sequenced. What does that mean? Bongo, go. Bongo, would you like my blanket? What does your bedroom look like? We'll spray it. We'll spray it.
Yeah.
Just the negative habits from it. That was a week ago. It's okay.
What happened a week ago?
It's just going to get tested.
You went to get tested.
It was actually 2 weeks ago.
And what I want to know is, because I'm dead scared of this testing, did they push something up your nose?
I don't know.
Mine was pushed up my nose.
Mine was also pushed up my nose. Mine was
It was pushed up your nose.
so wasting.
Okay, no, I'm not getting tested. I'm just going to die. So guys, if I just die, just learn the work, do nicely. I want to hear from up there, down there, I don't care.
It's too traumatized.
I beg your pardon?
You can't write a bio exam. It's too traumatized.
Oh, rubbish. Just go. Now we can be taught by somebody who's not nasty to us. Okay, sequencing genomes. Bongo, now that you're warm, what does that mean?
Like non-present sequencing.
What?
Not integrated.
No, go. I didn't hear you.
You go ahead.
Yes. What does that mean?
Oh, you mean like?
Yes.
It's really like
Sequencing the nucleotides of the DNA
Yeah.
of the organisms. Okay, right. So modern technology has enabled that to happen, and computer software has been developed to analyze relationships between genomes. Because if two organisms or types of organisms have got very similar DNA sequences, then they're more closely related than organisms that have got more diverse. If there's lots of differences, not so closely related. Okay. So the field of what is called comparative genomics, it just means comparing these things, supports the theory of a common ancestor with changes that have happened since then. Okay, right. So scientists have concluded that there was a common ancestor which had all the original genetic information, and some of these organisms experienced mutation events, and you know what that means. which led to some of them to occupy different ecological niches. In other words, they were better adapted for surviving in different ecological niches, and so speciation occurred. Which is a hell of a lot of big words. And it's really very, very simple.
So that's
Because there were mutations that occurred, it meant that the organisms were no longer all identical to each other. And because they were no longer identical, they were able to actually occupy different roles and different areas in the environment. Okay, so if I had evolved from somebody who was tall, then I would be able to live in a forest without hitting my head. But the tall person wouldn't have been able to. So if I came from a whole group of tall individuals, they've got to live on the grassland, sorry for you, whereas I can go and live in the forest because I'm like a midget. Does that make sense? Okay. All right. So now whole genomes are being sequenced and the field of comparative genomics has been beginning, and this concept of common ancestors is currently the theory that most scientists use today. Right, evidence for evolution, field 3, structural similarities. Okay, and this is important. So if you are asked to answer something where they say give 2 fields of evidence, I would give this one, and there's one down here that is one of my absolute favorites, but we'll talk about it. Okay, structural similarities. Now this you have to know. But let me explain it before you actually go, I have no idea what this woman is talking about. I need to tell you 2 different things. So the one is what are called homologous structures. Now you know this word homologous, because you know it from homologous chromosomes. So homologous structures are structures that are similar structurally, but have different functions. And an example is the forelimbs of mammals, birds, and reptiles. Mammals, birds, and reptiles have got exactly the same structure to their forelimbs. So your arm is the same as a chicken wing. And your arm is the same as a whale's flipper. Okay. So, this is evidence of what is called, new word, divergent evolution, which is the same as adaptive radiation. Okay, so remember, yesterday I spoke about adaptive radiation. Another word for that is divergent evolution. So when a group of organisms or a common ancestor evolves into a whole variety of totally different organisms. So the flipper of a whale, so this thing, and the wing of a bat, and your arm, and a bird's wing, and a reptile's forelimb, or front, or hind limb, all identical in structure. If you look at that, and this is referred to as a pentadactyl limb. What does penta mean?
5 fingers.
5. Dactyl means fingers, and it's a 5-fingered limb. But although we're talking about 5 fingers, in reality, it actually refers to the entire structure. Now remember, you learned about there's a humerus, and there's a radius and ulna, and carpals, and metacarpals, and phalanges. Or if you look at the hind limb, a femur, a knee, tibia, fibula, tarsals, metatarsals, phalanges. Okay? Alright? So basically the hind limb, with the exception of the patella, the hind limb is exactly the same as the forelimb. Okay, you happy with that? Got the same basic structure. One big bone, 2 smaller bones that are parallel to each other, a whole lot of little bones that form the wrist, a whole lot of little bones, slightly bigger, that form the palm of the hand or the arch of the foot, and then the digits, the phalanges. Okay, so it doesn't matter whether you look at the wing of a bat, it's got exactly the same structure. There's the humerus, there's the radius and ulna, and then those are the digits. Okay, it's exactly the same with the chicken wing, it's exactly the same with the human forelimb. Okay, whether you look at a human or a cat or a whale or a bat, exactly the same. So these colours show that this bone and that bone and that bone and that bone. So they might have been modified in terms of how thick are they and how short are they, because those are definitely shorter than that one. And look at the phalanges here, much longer. Phalanges there, much longer. Okay, and carpals, metacarpals, longer here than our metacarpals. Okay, and carpals. Okay.
This is also evidence of evolution.
Yes, because that's what we do.
Yeah. Yes, but what would I call this?
Structural similarities.
Structural similarity.
End of second half hour, day 12, 22, 15 July 2020. I did.